Welcome to the 11th lecture for Physics 4B. We finally introduced Gauss's law, the first of what we will call Maxwell's equations, by the end of this semester, and give several examples of applications of Gauss's law. So, in the first video, we properly introduced Gauss's law. I hope the lab activity earlier building up to it helped, hopefully. And in the same video, we also take some time to define and talk about the electric flux, which is used to state the Gauss's law in the integral form. Then we have three examples of highly symmetric charge distributions, where the symmetry allows us to pretend to do the integrals needed for calculation of electric flux, but without actually having to do the integral. This is the better method with which to derive several useful electric field formulas. And from here on, we hold the direct integration method in reserve only for situations where the charge distribution is not quite symmetric enough. We wrap up this lecture set with some discussion of conductors, contrasting their properties to insulators, and introducing two of the properties of conductors that are useful in electrostatics analysis. We will introduce a couple more conductor properties next week. This completes our full introduction to electric fields. In next week's lectures, we will introduce electric potential, or as I will refer to it most often, voltage. In the last chapter, we introduced the Coulomb's law and the idea of electric field. And we applied them to calculate the electric fields due to various extended charge distributions, which was a lot, as you can see on the screen here. Now, I want to step back for a bit and consider the nature and character of some of the physical laws that we have seen so far, and along the way introduce a new law that you will see this week, Gauss's law. So let me give this a title, Introduction to Gauss's law. And we are going to talk about something called the electric flux. Coulomb's law is what we call an inverse square law. Square, because the strength of the electric field depends on the distance squared, and inverse because as the distance increases, the electric field strength decreases. That is, the electric field strength is proportional to 1 over r squared. And for most of you, this is not the first time you have seen an inverse square law. When you learned Newton's law of universal gravitation, there was another inverse square law. Gravitational force due to a point mass is proportional to 1 over r squared. In fact, inverse square laws are incredibly common. In particle physics, whenever we have a force or a field that decreases as 1 over r squared, inverse square law, we call that a long-range force. So that has to make you wonder, is there some physical significance to that 1 over r squared relationship? In a way, there wouldn't be for a 1 over r or 1 over r cubed relationship. We can look at another phenomenon that has a kind of inverse square law. We haven't officially looked at it before, but I think it's intuitive enough for people to just to think through. Imagine that you have a 60-watt light bulb in the middle of a big empty space. Every second it's on, it emits 60 joule of energy in the form of light, visible and infrared. Consider how bright this light bulb would appear 1 meter away, and compare it to its brightness, for example, 2 meters away. We measure intensity, one of the ways to measure brightness, as amount of power going through some area per area. If the 60 watt of radiative power is going through 10 square meters, for example, then the intensity would be 6 watt per meter squared. With Nothing more than a couple basic principles, like a conservation of energy and the geometry of three-dimensional space. You can figure out how the intensity of this light bulb should change with the distance. Consider some volume containing the light bulb. If energy is conserved in the space the light bulb is in, then an equal amount of energy should leave the space each second, as radiative energy enters through the light bulb. Each second the light bulb emits 60 joule of energy. This energy should leave the volume containing the light bulb each second. And this statement would be true for any volume. So we could consider a sphere of radius 1. Or we could consider a sphere of 2 meter radius, but let's stick to 1 meter for now. Finding the intensity of the light bulb at this distance is as simple as taking the total power of the light bulb, 60 watts, and dividing by the surface area of the sphere, having radius r. That would be 4 pi r squared for the surface area of a sphere. This would be r. 1 meter or r. This is assuming that the light bulb emits light omnidirectionally. Now, if you are looking at the intensity at 2 meters away, since the surface area of a sphere of radius 2 meters is 4 times the surface area of a sphere with a radius of 1 meter, from surface area 4 pi 1 meter squared, comparing that with 4 pi 2 meter squared, the intensity at 2 meters away is 1 over 2 squared times intensity at 1 meter away. In other words, this intensity obeys a kind of inverse square law, following from this dependence of the area that the radiative power would go through. Note the simplicity of this argument. It doesn't depend on some complex details of how light travels. It only depends on a conservation law. Once the radiative energy enters the volume through a source, the light bulb, it has to leave the volume somehow. It can't simply disappear. That the intensity of light should follow an inverse square law is a natural consequence of our three-dimensional universe. Can electric fields be thought of in a similar way? The following is the line of thinking you might go through. Think about the electric field lines you learn to draw. If you have a positive charge somewhere, we draw these lines as coming out of that positive charge. And these lines go on forever. One of the rules that we have for drawing electric field lines is that the field lines begin on a positive charge and end on a negative charge. If you don't have any negative charges, then you can't end these lines. They have to go out to infinity. We could almost say electric field lines are conserved. We don't quite say that. But in any case, electric field lines can't just disappear. And if you have some positive charges in some space and you count, say, 1, 2, 3, 4, 5, 6, 7, 8 electric field lines coming out of it, whether you count them going through a small volume or a large volume, you are going to count the same 8 lines. How will this help us come up with a new law? We can think in analogies. Imagine that the positive charge is like a light bulb, and the electric field lines are like rays of light coming from the light bulb. The strength of the electric field is indicated by how densely packed the electric field lines are, and the intensity of light is indicated by how densely packed the light rays are. In the example with the light, the intensity itself wasn't conserved. It followed the inverse square law. But the power was. The same 60 watt of power had to leave the volume regardless of its size. So with the electric field, while the electric field itself isn't conserved, it follows the inverse square law. A quantity we can associate with the electric field times area might be conserved, in a way similar to how we always count 8 field lines for a positive charge, regardless of the volume we use. we do define a quantity that is a kind of electric field times an area, and we call it flux. And because we don't have the same intuition we have for this flux that we have for radiative power going through an area, we have to be careful. Let me give this a simplified example. Let's say we have uniform beam of light, and we have these two square areas, one oriented this way and another oriented this way. Does the same amount of radiative power flow through these square areas? I think most of us intuitively know that the answer is no. In fact, if we turn this square surface so that the light rays are going parallel to the surface, we can see that no light is going through the surface. So when we say power is intensity times area, it's not a multiplication between two scalars. In fact, it has to be a multiplication between two vectors, maybe a dot product. Going back to flux being electric field times area, we already introduced the electric field as a vector, and we can use it as it is. But how is area a vector? Or more precisely, we can see that when we have a surface area, we can see that something is physically changing when you rotate it. You can see that orientation of surface in space has a meaning. But how do we express that mathematically? If you are thinking of a vector that is in the plane, no single vector will do the job. When I talked about light rays going parallel to the surface, I think we were intuitively thinking of a vector that is in the plane and that is parallel to the light rays. But there are also vectors tangent to the surface, going this way, that is in the surface, but it's perpendicular to the direction of the light rays. And if we accidentally pick one of these vectors, we'll have a very wrong idea about how the surface is oriented relative to the light rays. And we have the same problem when we are considering the electric field times area. What will in fact work is a vector that's perpendicular to the surface. So with a surface like this, I would be looking at vector that's perpendicular. And as I imagine rotating the surface, the vector would remain perpendicular to the surface and stay that way. By the way, depending on your Physics 4A class, this discussion might have been covered when they covered the cross product, which Physics 4A uses to handle the rotation of rigid bodies. The set of all lines that are perpendicular to a particular given vector, it defines a surface oriented in a particular way. Here in this picture, it would be this surface that's perpendicular to this given vector. And we call this given vector surface normal. Normal here just means perpendicular. It's a bit of a peculiar usage of terms. So when I talked about light rays going parallel to the surface, if I wanted to make that mathematically precise and not rely on your intuitive mental picture for the situation, I would instead say light rays going perpendicular to the surface normal. And there's an elegant simplicity here. If I define radiative power going through some surface as intensity, dot product with some area, where the direction of the intensity vector is in the direction of the propagation direction of light, and direction of the surface vector is in the direction of the surface normal. In the situation where the surface is perpendicular to the light, so we get the maximum power going through, the I dot A will be at maximum because they are parallel. And in this situation, where the surface is parallel to the direction of the light rays, the dot product I dot A will be 0 because they are perpendicular. So this precise mathematical description gives physically reasonable results. So electric flux through a surface is defined similarly as electric field dot product with the surface vector. Flux V is equal to E dot A. Let's practice using this definition of flux with a few simple geometries. We know a point charge produces radially outgoing field lines. Let's pick a distance r, at which point we measure electric field E as a function of r. And if we put together the set of all points that are at distance r, that becomes a sphere of radius r. Let me try to draw this sphere here. What is the electric flux through this spherical surface of radius r? If we simply did flux is equal to electric field times area, and did phi is equal to electric field E times 4 pi r squared. 4 pi r squared being the surface area of a sphere. Well, that is the correct answer. But we might miss some subtleties that's important elsewhere. So let's be careful from the start. When you go from one part of sphere to another part of sphere, a lot changes. The direction of surface normal vector changes, for one. So instead of writing down the electric field dot product with the surface area for the whole sphere, what we can do instead is write it down for a representative surface element of an infinitesimal size, dA. Then for this surface element, we can look at the surface normal vector and see that it points in the same direction as the electric field vector, radially outward, and work out the expression E dot dA. It's just the EDA. Because the two vectors are parallel, the dot product just becomes the product of the magnitudes of the two vectors. And the vector cosine theta that would be there, that's just 1, because theta is 0. Now, imagine doing this for every surface area element that covers the whole sphere. It's a lot, so I'm not going to draw them all. But doing that is what gives us the integral over the sphere of E dA. And that should be the total flux. Now, here's the magical part. Because we are on the surface of the sphere, which is all at distance r from the point charge, the electric field strength E is the same everywhere on the sphere. Meaning it's a constant. We can pull it out of the integral. This integral just becomes E times integral of dA over the sphere. And we already did the dot product, so these are both just the scalars now. And we already know this integral. That's the surface area of a sphere. So that's 4 pi r squared. Make sure to multiply to the coefficient E for the flux. So the electric flux through the spherical surface in this example is E times 4 pi r squared. E times 4 pi r squared. As I said, it is the correct answer, but I want you to go through this reasoning process. Now, let's cover a slightly more complicated example. We'll keep the point charge the same. Let me draw the field lines. And instead of a spherical surface, let's imagine a cube of side L. And if we want, we can make this L equal to 2R to make the situations above and here now comparable. And it's the same question. What is the electric flux? And if anyone's thinking, that's simple. Each phase is at distance r from the charge, and the area here is L squared. So the flux through each phase is E, same E as above, times L squared. You got 1, 2, 3, 4, 5, the front, 6, the back faces. So the total flux is E times 6L squared, or in terms of R, since L is equal to 2R, E times 2R squared, 4R squared, 4 times 6, 24, 24R squared. And that's the answer. No, that's not the answer. This is why we went through the first example with some care. Let's look at some representative surface area elements on the cubic surface. I'll use this top surface for examples. When I did this calculation, I was thinking of this surface area element right at the center of a face. It's a distance r away from the positive charge, and the surface normal is pointing radially away from the charge. But this face has other surface area elements, like this one near the corner. This is not distance r away. This should be, I think, square root of 3r away. And the direction of the surface normal vector and the direction that's radial, they are no longer parallel. This angle isn't 0 anymore. And the dot product, E dot dA, is no longer very simple. And this will depend on where on the face you are. Now we could go through a corrected, detailed calculation, fixing these issues. Maybe. But let's step back and compare this picture of the electric flux through a cubic surface with this picture of the electric flux through a spherical surface. For the sphere, we calculated E times 4 pi r squared for the flux. Should it be different for the cube? Both the surfaces have the same number of electric field lines going through them. 8 here and 8 here. This is the kind of conservation law that we are talking about. Intuitively, I think the electric flux through this cubic surface should be the same as the flux through this spherical surface. Because once these electric field lines are sourced through the positive charge, it has nowhere to go except through a surface enclosing the charge. And so on. And similarly, if this spherical surface area was small or large, it shouldn't affect the flux we would calculate. The electric flux we calculated before might make it look like the flux depends on radius r, because the flux is equal to E times 4 pi r squared. But this electric field E is a function of distance r, according to Coulomb's law. E is equal to Coulomb constant times Q, the amount of charge, divided by r squared. Plugging this into the flux, we can see that the r squared in the denominator canceling out with the r squared in the numerator, that the total flux through the spherical surface is equal to, let me rearrange the terms a little bit, Q times 4 pi times Coulomb constant. Your textbook and many other textbooks define a new constant called permittivity of free space, or electric constant, or written as epsilon naught, that is equal to 1 over 4 pi times Coulomb's constant. To write this quantity as Q over epsilon naught. These are the simplified expressions for the flux, and the R dependence is gone. Now, let's formalize this intuition. We used examples of spherical and cubic surfaces. But if our intuition about conservation of electric field lines is right, the result shouldn't depend on any particular shape of the surface. The only thing we should need to know to calculate the total electric flux out of a volume is how many sources of electric fields, the positive charges, are inside the volume, minus the sinks for electric fields, negative charges, where the field lines can end without exceeding the volume. This gives us Gauss's law. The electric flux out of a volume, or the closed surface integral of E dot dA, is equal to what we calculated using the example of the spherical surface. Charge enclosed times 4 pi Coulomb constant. Or, if we are most textbook authors, charge enclosed, divided by epsilon naught, or permittivity of free space, or electric constant. It's a highly abstract, highly mathematical law. So I want you to do it some justice, introducing it properly. We are going to spend some time applying the Gauss's law to driving electric field formulas in other lectures. What I want you to keep in mind are, 1, whenever we are applying Gauss's law, what we are secretly interested in are the electric fields, not the flux. In fact, there aren't that many applications of electric flux other than in stating Gauss's law in its integral form. 2, symmetry, symmetry, symmetry. The derivation of electric fields applying Gauss's laws looks almost like magic. You say a few right words and you're done. The process that makes this amazing simplification also mathematically rigorous is the argument appealing to symmetry. And especially for those of you who may become a physicist, go to physics grad school and all that, these symmetry arguments are well worth paying attention to. I think that's all. Thank you for watching this long lecture to the end, and see you in the application of Gauss's law lectures. Hi, this is the first video on applications of Gauss's law. So you have looked at Gauss's law and how it makes intuitive sense. That when you look at the electric charge as being the source of electric field, that electric flux is in some sense conserved. Graphically, this is easiest to see in an electric field line diagram. The electric field lines come out of a positive charge, and it can either go out to infinity or end on a negative charge. And this quantity here, electric field times the area, is in some sense counting those electric field lines going through a particular area. So once you have, for example, a positive charge, and you have a surface defined that's enclosing that positive charge, then this electric flux, number of electric field lines going out of the surface, really only depends on the amount of charge that's enclosed. It doesn't depend on anything else. Now, what takes more work is seeing how this is useful, because we don't usually care about quantity like a flux. It doesn't really relate to anything that you would measure physically. So it's a question of what is Gauss's law good for? A lot of what we do in electrostatics is trying to find electric field. Gauss's law has electric field in it, so it looks like it might be useful in finding electric field. But the challenge here is that this is inside an integral. As you might remember from your calculus class, when you have an unknown function inside an integral, it's really difficult to solve for that unknown function. So as far as applications of Gauss's law goes, what will be really important will be symmetry. Because if you have symmetry, this is what we might be able to do. We might be able to make an argument that this electric field is constant over some area we are dealing with, and then we can pull this out of the integral, thereby avoiding the need to do any actual integral and solve for the electric field. So here's the good news. With the applications of Gauss's law, there will really only be 3 types of symmetry where you can actually exploit that kind of uniformity to pull the electric field out of the integral and be actually able to solve for the value of the electric field. And we'll go over all 3 examples. That's what this and the next 2 videos are about. So in this first video, I want to look at the spherical symmetry. If you remember the other lecture videos, You might remember the sphere example being the most difficult example. Now with the Gauss's law, the exact opposite is true. Spherical symmetry actually represents the simplest kind of symmetry. This is where we have rotational symmetry in all three dimensions. So this is what a sphere looks like. You've seen it. And this is what we mean it's rotationally symmetric. When we take a sphere and we rotate it, nothing changes. And you can do this for three different axes, which is what I mean by rotational symmetry in 3D. This symmetry, when you have it, gives us a very strong argument for simplifying the expressions involving Gauss's law. So let's get started. Let me use the simplest possible example of uniformly charged sphere. So suppose I have a sphere of charge and it carries a uniform charge density rho naught, a constant. So this is a spherically symmetric. You can take this, rotate it around any kind of axis, and nothing changes. And we'll see soon just how useful this fact is. Let's say this sphere of charge has radius r. The question we are most interested in here is what is the electric field? And we have some sense it's going to depend on the distance from the sphere. So as a function of distance r from the sphere. So let's take a point outside the sphere that is at this distance r. For this case, we can say that this lowercase r is greater than the radius of a sphere. And we have done this calculation before, last time using integral. And this time we are going to somehow try to use Gauss's law to answer this same question. And the first thing about Gauss's law is that it involves an area integral over a closed surface. So we are going to need to define a surface. We call this surface Gaussian surface. It doesn't correspond to any physical object. It's just a mathematical surface over which we are going to do this integral, or pretend to do this integral. So since we want to find the electric field at this point, we better define a surface that includes this point here. And the key to choosing a useful Gaussian surface is to choose a surface that follows the symmetry of the setup. Here we have a spherical symmetry, so we should choose a spherical surface that includes this point. So let me draw that. Alright, here's the spherical surface that contains that point. So it's a sphere of radius r. Now with this spherical surface, this is the argument we can make. We can say that the electric field at this point here is going to be the same as electric field magnitude at this point here. Because this is what we are imagining. Take a sphere with this dot here, and we can do what we call symmetry operation. We can apply a rotation operation that's going to take this point to appear. And when we do that, with this system, nothing changes because this charge distribution is spherically symmetric. The rotation changes nothing, which means the electric field also shouldn't change. So this is the gist of that symmetry argument. And let me add in this detail of the area element. So from when we covered electric flux, you know that with the area element, we assign a vector direction so that the vector direction points perpendicular to the surface. So at this point, when we look at E dot dA, we are looking at the dot product between the electric field and this area element, dA. And we can come up with a symmetry argument that will let us say that the electric field must point in the same direction as dA, radially outward. This is the argument. Let's suppose, for the sake of argument, that our electric field somehow doesn't point radially. is some goes in weird direction. Then this is the symmetry operation we can consider. We can imagine reflecting it over a line connecting from center to that point. And when we reflect it over, what it would do is it would change this electric field so that it points this way. But part of the spherical symmetry here is that when you do that reflection, the charge distribution doesn't change. So this change of electric field is absurd. It's contradictory, which is why we call this proof by contradiction. The thing that we started assuming leads us into contradiction, which means what we assumed must be false. So instead of assuming that our electric field can point in some direction like this, we have to undo that assumption and say that the only direction electric field can point in is in the radial direction. So that when you do the reflection operation, the electric field doesn't change either. So this argument that I sketched out here, the combination of two things, that the magnitude of electric field must be constant over this entire surface, and moreover, electric field must be parallel to the area element dA, simplifies this integral a lot. Let's see. So we have E dot dA, but we know electric field is always parallel to dA. So this dot product becomes just a product of the two magnitudes, E and dA. And we just made the argument how over the entire sphere, the electric field is constant. So I can pull the electric field out of the integral to give us electric field times the integral of dA over the sphere. Well, that's just the surface area of a sphere. Hopefully you have that formula memorized. Surface area of a sphere is 4 pi r squared. Here, lowercase r, because that's the radius of the Gaussian surface we are looking at. I want you to see how quickly the left-hand side simplified into this simple algebraic formula with no actual integral at all. And what we can now say is that this left-hand side is equal to the right-hand side. So this is equal to charge enclosed multiplied by all these constants, 4 pi times Coulomb's constant. And we can solve for the electric field. Electric field is equal to charge enclosed. The 4 pi's cancel, so times Ke, Coulomb's constant, over r squared. This should look familiar because this was Coulomb's law. Now what's different here is Coulomb's law was for point charges. This is electric field of a sphere outside of the sphere. I hope this reminds you of a result that we are using in physics 4a without derivation. That gravitational effect of a spherical body, you can calculate that by treating the sphere as if it's all concentrated at the center of the sphere. This calculation is the proof why. In anticipation of the next case we are going to look at, we can change the parameters for our answer here because we are given the uniform density instead of the total charge. And this is a pretty simple calculation. The charge density is the amount of charge divided by the volume of the sphere. So charge enclosed or charge in the sphere is just the density times volume. And hopefully you have this memorized. Volume of a sphere is 4/3 pi r cubed. And here I want to use the correct r. I need to use the radius of the sphere, not the Gaussian surface. So plugging this in for charge enclosed yields this result. Electric field of the sphere on the outside is 4 pi Coulomb's constant r cubed, the density of the sphere, divided by 3r squared. Well, this doesn't look any simpler, But as I said, I'm anticipating the next case we are going to look at. So we found the electric field of spherically uniform charge distribution. But this is only a special case of where the point is outside the sphere. Now, what if the point is within the sphere? So we would be looking at, for example, this point here. Let me call that B. How would we calculate the electric field at point B? And the steps we go through is remarkably similar to what we just went through. So the first thing we do is define the Gaussian surface that contains that point and honors the symmetry of the system. So that's going to be another sphere. Sphere of radius r. This time, this radius is less than the radius of the charged sphere. Alright, let's step through the calculation we did. The left-hand side of Gauss's law, calculating the flux. The symmetry argument we made before continues to hold. So none of these steps are changing. Alright, so this left-hand side, it remains the same. The flux is electric field times 4 pi r squared, the area of the Gaussian surface. So what changes? What changes here is the charge enclosed. You can see it in the picture here. I'm leaving a bunch of charge on the outside. So I have to put in the correct value of charge enclosed to get the correct result here. So let's look back at how we calculated the charge enclosed. It was charge density times volume. So before I used the volume of the whole sphere using the radius capital R. Now this time what I hope you see is that we want the volume of only that enclosed within the Gaussian surface, because that's the only charge that's enclosed. Outside the Gaussian surface, these are not charges enclosed, so we can't include them. So going back through the derivation, there it is. Instead of capital R cubed, I would put in lowercase r cubed. That's the radius of our Gaussian surface. So plugging that in for Q enclosed, I get instead of capital R cubed, lowercase r cubed. And that actually leads to some interesting cancellation. I still have this lowercase r squared from calculating the flux on the left hand side and then moving it over. So this is going to cancel out two of the factors here, leaving us with this result. It's a remarkable result. It says simply that the magnitude of electric field inside the sphere, it goes linearly as the distance from the center of the sphere. So when you're at the very center, the electric field is 0. When you hear that, it probably makes sense. I hope it makes sense. And as you go farther and farther out, the electric field increases up until the point you reach the surface of the sphere. After you reach the surface of the sphere, then the electric field decreases as inverse square. So that's the result. So with these two results, I know the electric field over the entire space around the spherically uniform charge distribution, and that's our result. I want you to notice how much simpler this was compared to the integral calculation that I did last week. That took 30 minutes. I had to use Mathematica. Here, all this was very simple. And if you've been paying attention to the argument, it is mathematically rigorous. I have taken no shortcut, no hand-waving arguments that cannot withstand the scrutiny. Before we move on to the next example, I want to look at one significant result that I just mentioned in passing, but I want to highlight it so that you will remember it the next time you need to use it. Let me clean up the figure a little bit here. Now, this time, instead of saying uniformly charged sphere, let's say we are dealing with a uniformly charged spherical shell. So all the charge is sitting on the shell here, and it's uniformly distributed. And I think if we ask for the electric field outside, you can get this result in the same way we just did the calculation. You can go through the same calculation for radius greater than the radius of the sphere, and I hope you can walk through that on your own. Now, here's the place where it gets interesting. Let me ask, what is the electric field inside the spherical shell? Alright, so that means we define a Gaussian surface here, a sphere of some radius that contains the point that I'm interested in, possibly. And when you go through this argument, you are going to see that the charge enclosed is equal to 0 because it doesn't enclose any charge. And here's the power of the symmetry argument. Nothing on the left-hand side here changes. So I can say when the enclosed charge is 0, you can say, looking at the rest of the equation, that the electric field must be equal to 0. So here, we can say that the electric field here is equal to 0. And this is not a statement that you can make every time. We went through carefully how you could have 0 flux and yet have non-zero electric field, because flux is integral, and you can have a non-zero integrand that integrates to 0. So what I'm telling you now is that when you have high enough degree of symmetry, like this spherical symmetry, you can say that when your flux is 0, the electric field is 0 also, because there's this step where we are able to take the electric field out. So at this point, if we are still saying that the flux is 0, then well, electric field has to be 0. So this is the result that I wanted to highlight for you, that electric field inside a uniformly charged shell is equal to 0. So the derivation is interesting. If we had to do this by integral, I can tell you that it would have taken a lot of work and would have been very difficult. With Gauss's law, it's a very simple argument we had to go through to be able to claim this very broad statement. And the second thing is, this arrangement is surprisingly common. Whenever you have a conducting sphere and you put some charge on it, the charges are going to spread out in a uniform fashion. So when we get to conductors and we are dealing with the spherical conductors, I hope you remember this fact so that you know that electric field inside a uniformly charged spherical shell will be 0. Alright, so that's everything I have for the spherical symmetry. In the next video, we'll look at cylindrical symmetry. Hi, so we are continuing with applications of Gauss's law, and in this video, instead of the spherical symmetry, we'll look at cylindrically symmetric cases. And cylindrical symmetry is a bit difficult to describe as just rotational symmetry in 3D. So let me draw the figure and highlight some of the symmetries that we can observe. So here's my cylinder. It has a circular cross-section, and even though it looks like I'm drawing it finitely, really what you should understand is that this is an infinitely long cylinder. It continues on without limit. I was really only drawing those circles as an indication of the cross-section. So with a cylinder like this, we have two clear symmetry operations we can do. One is rotation. But unlike with a sphere, I have only one axis of rotational symmetry. I can rotate this cylinder around this axis and nothing will change. So that's one. And we gain a new type of symmetry with a cylindrical geometry here. As long as we have an infinitely long cylinder, we have what's called translational symmetry. That means we can take the cylinder and if we translate it, we don't change anything. Now, for a finite cylinder, you can see that it's clearly not true. You translate it, you have moved it, you've changed the things. But with an infinitely long cylinder, when you move it a little bit up or down, you haven't changed anything because it still goes on forever. So those are the two symmetries we are going to exploit to help us use Gauss's law to solve for electric field in this setup. So we have the same question as before. What is the electric field, both outside and inside the sphere? Let me give the sphere a radius of r, capital R. Alright, let's do the easy part first. Let's say we want to know the electric field at this point here, where the distance r, lowercase r, is greater than the radius of the cylinder. Then our first job is to find the closed surface that honors the symmetry of the system. So I have cylindrical symmetry, so I should pick a cylindrical surface. Now, here's a bit of a wrinkle in the plan. We can't have this Gaussian surface be an infinitely long cylinder, because then it won't be a closed surface. The one part of using Gauss's law you have to remember is that it only applies to a closed surface. So you have to close up the surface somehow so that we can actually use Gauss's law. And the way to do it is to actually close it up with these end caps that I drew here. So instead of this being just an indicator of the cross-sectional area, I just say, well, that is my actual closing surface, top and bottom. And the side surfaces close up the rest. So I have a cylindrical, finitely long closed surface. So this is where it's useful to draw electric field lines. When you look at this long line of charge, really the only kind of electric field line that makes sense is this one. The electric fields are going in the radial direction away from the cylinder. And if you want, we can go through the same argument, proof by contradiction as before, to show that an electric field that looks like this is impossible. You assume this impossible case, then what you can argue through is, well, I have that reflection operation as a symmetry operation. So you do reflection, nothing in the charge changes, but the electric field has to go from pointing up to pointing downward. That's absurd, so that's contradictory. So that means our initial assumption was wrong. Electric field can't be pointing up or down. It has to only point radially outward. Now, this gives us an interesting possibility. Even though we had to close up this top and the bottom surface to be able to say we have closed the surface, looking at this electric field line here, we can see that it's going to work out so that the electric flux through the top surface is 0. None of the field lines go through it. And the electric flux through the bottom surface is also 0. So really the only thing we need to worry about is what is the flux through the side surface. So let's work through that. This is what left-hand side in Gauss's law says. And from the argument that we just went through, we can say that this is no longer integral over closed surface, but integral over just the side surface. Now, along the side surface, this is what we can argue. We can argue that the electric field magnitude is uniform over the whole side surface. We can see that from translational symmetry that the electric field magnitude here should be equal to the electric field magnitude there. Otherwise, you don't have translational symmetry. And from the rotational symmetry, the electric field at one point there, electric field at another point here, electric field here, here, they are all going to have the same magnitude also. And like with the sphere, we have a happy coincidence that here the area element is directed in the same direction as the electric field. And just to reiterate, the area element at the top and the bottom surface are perpendicular to the electric field and contribute zero contribution to the flux. Alright, I think that means here we can get rid of this dot product, say that we are just dealing with the magnitude of the electric field times the area element for the side surface. We just made the argument that the electric field is uniform over the surface, so we can pull it out of the integral. So the only thing we are left with is integral over the side surface of the cylinder. Well, I have the circumference, which should be 2 pi r, lowercase r because we are looking at the Gaussian surface, times the, I guess I have to give it some parameter, times some height, h. So this is the left-hand side. Electric field times 2 pi r h is the net flux out of this cylindrical Gaussian surface. Now let's look at the right-hand side. So for the right-hand side, we are looking at charge enclosed times a bunch of constants. Now for this charge enclosed, it can't be the charge of the entire wire, because then wire being infinite, it's going to be infinite amount of charge. We really only mean the amount of charge enclosed within the Gaussian surface we defined. So we need to figure that out. So here we would need some kind of a density. We could do the same thing we did with the uniformly charged sphere. We can say for the uniformly charged cylinder that it has a uniform charge density rho 0. Then I think I can express the amount of charge enclosed in terms of this density and the volume, which should be the area of the cross section, pi r squared, times, this is where this parameter came useful, height. Alright, let's look at what we get. So I'm going to solve this expression for electric field, plugging in charge enclosed as I go. So the electric field is equal to a whole bunch of constants divided by the factors from the left-hand side. 2 pi r h. Ooh, this h cancels. That's good because it was an arbitrary height that shouldn't have any physical meaning, so I was hoping that it would cancel out, and it does. So we have this as a result. Electric field outside a cylinder is equal to a bunch of constants times 1 over r. And this is what I want you to notice, that with an infinitely long cylinder, the distance dependence of the electric field magnitude goes as 1 over r, not 1 over r squared. And we can do a little more simplification. Let me do that for the version I'm going to write down here. Now, we actually derived all this using integration over the charge distribution. So what's really going to be new here is the exact same situation we looked at for the sphere. What would be the electric field, for example, for a point inside the cylinder? So we are looking at where radius of the Gaussian surface will be less than the radius of the charge. So this is the Gaussian surface that contains that point. Alright, let's step through each step in the calculation and see what we need to change. The left-hand side, the starting point never changes. And it looks like we are still keeping the top and bottom surface, the flux through those two be 0. So this closed surface area integral is really this open surface integral. And the exact same argument we made for the symmetry of electric field still applies inside the cylinder. So this step is still valid. The surface area of the side surface of cylinder, that's not going to change. So it looks like what will have changed is exactly the same thing we are dealing with for the spherical case. We have to work out the enclosed charge again. So with the radius of the Gaussian surface less than the radius of the charge distribution, what we need to say is that charge distribution, we are not looking at the cylinder of radius capital R. We are really looking at the radius of lowercase r. So let me write that down. Alright, plug in for Q enclosed. So that changes this capital R squared into lowercase r squared. Oh, I think that means there's a cancellation. This factor of 1 over r that we had before, it cancels out with the one factor of r. And this is the answer that we are left with. So the electric field is a bunch of constants times r for the distance from the axis of the cylinder less than the radius of the cylinder. So there's an interesting coincidence between what happens for the electric field inside the charge distribution. And we seem to be getting very similar results for the sphere and the cylinder. And I hope that makes intuitive sense, because if you're along the axis of the cylinder, then your electric field would be zero due to symmetry. Alright, that's everything I had for this geometry. In the next video, we'll look at last of the 3 symmetrical geometries where we can use Gauss's law, and that'll be the planar geometry. Until then, bye. Hi, this is the last of the videos looking at applications of Gauss's law. So in this video, instead of looking at spherical or cylindrically symmetric arrangement, we are going to look at geometries that exhibit what you might call rectangular symmetry or Cartesian symmetry, or you could call it planar geometry. So here, we are not looking for rotational symmetries anymore. Instead, this is what the geometry looks like. Let me draw 2 views, a perspective view and a side view. Sort of imagine bring up the plane and you're just looking at it at the light level. We can say that this charge distribution has uniform surface charge density, sigma naught. So if we are dealing with an infinitely large plane, this geometry has translational symmetry. It has translational symmetry for 2 directions. Basically, the 2 directions that the plane is not perpendicular to. Because for those 2 directions, you can move the infinite plane however much, and nothing will have changed. And as before, it's useful to draw electric field lines to kind of see what kind of symmetry you can exploit exists. And as before, we can use a symmetry argument to prove important features of these field lines. For example, we can prove that there's no concentration of field lines in one area, because if it did, it would violate the translational symmetry. You translate the whole system, charge distribution doesn't change, but this special region needs to move. So you can say that electric field as a function of x or y is constant. That's the only way you can obey the translational symmetry. And we can continue to use reflection symmetry to rule out weird looking electric field lines like this. Then we imagine doing reflection that flips everything around, flips the electric field around, but the charge distribution didn't change. That's contradiction, so can't happen. So this is the electric field lines that we are left with that's consistent with the symmetry of the system. Now, the question as before is still the same. What is the electric field? And to use Gauss's law, once again, we need to define a Gaussian surface. So let's say we are looking at a point here. We are looking at what is the electric field at this point. And since we have a rectangular symmetry, we are going to need to pick a rectangular surface. So from this side view, that surface will look like this. It's very carefully chosen. I will go over it in a little bit. Or let me draw this in the perspective view so that you have some idea of what the three-dimensional shape of this Gaussian surface is. It's what's sometimes called matchbox style surface. You have top and bottom bases. It can be any shape. I prefer the rectangular shape. Here, really, those top and bottom surfaces are what we want. But to be able to apply Gauss's law, we need to connect them into a closed surface. That's really why the side surfaces exist. But as before, you see the surface normal, the surface area element, points in a direction perpendicular to the electric field. So the flux through the side surface here will be 0. And true of all the other side surfaces. You are only really looking at flux of the surfaces at the top and bottom. And I want to be extra careful here. And I want to say that I arrange this Gaussian surface in such a way that this distance here, call it G plus, is the same distance here, G minus. Because I want to be able to say, based on the reflection symmetry, that the electric field magnitude here must be the same electric field magnitude here. Otherwise, it would violate the reflection symmetry that you see. Okay, so with all those symmetries pointed out, let's go through the same motion as before. We were pretending that we are going to do the left-hand side integral of Gauss's law. And through the symmetry argument we made, we could reduce this down to essentially the integral over the top and bottom surfaces of the Gaussian surface. The side surfaces gives 0 contribution to the flux. And we can see as before, the area element here is parallel to the electric field. So we can get rid of this dot product. And as we went over, along the top surface, the electric field has to be constant as to obey the translational symmetry. And the electric field along the top surface has to equal the electric field along the bottom surface so that the reflection symmetry is obeyed. What that adds up to is that this electric field value here is a constant. I can pull it out of the integral. So it's an integral over the area element of the top and bottom surfaces. Okay, so to be able to do this integral, I need to specify some parameters. Let's say that these top and bottom surfaces had area A. As I said, the shape doesn't actually matter. So I have 2 of those surfaces. So the left-hand side of Gauss's law becomes electric field times 2A. That's equal to the right-hand side. Here, the charge enclosed would be this amount of charge here. And in terms of given parameters, the charge enclosed should be the surface charge density times the area. So the right-hand side is bunch of constants times, more constants. Let me finish the solution here. Solving for the electric field, I get 2 pi Ke sigma. The areas, the arbitrary parameters, having been cancelled out. This is a very interesting result for infinite plane electric field, that it's constant. It's not a function of distance. If the plane is truly infinite, then you can be as far away from the plane as you want, and electric field won't change. In practice, what this means is, as long as you are close enough to the plane to be able to consider the plane as if being infinite, the small amount of distance change here doesn't change your electric field. You need to be far enough away that you can no longer consider the plane to be infinite. So that's the result. In the version with the permittivity of free space, epsilon naught, this would be sigma over 2 epsilon naught. I just want to point out one thing here, because later on you are going to see a similar looking but slightly different result. Later on you are going to see that electric field outside the conductor is equal to sigma over epsilon naught, or 4 pi Coulomb's constant sigma. So you might wonder, what happened to the factor of 2? This is what I want you to remember. With the conductors, the electric field inside the conductor is 0. So if you have electric field here of magnitude sigma over epsilon naught, look at the difference in the electric field. It's the same difference you see between the top and the bottom regions. At the top, the electric field is plus sigma over 2 epsilon naught, pointing up. At the bottom, the electric field is minus sigma over 2 epsilon naught, for the difference in electric field of the same amount, sigma over epsilon naught. Really what this is with the conductors, there are other charges in the parts of the conductor that I didn't draw. From those charges, if I didn't have this surface here, I would have gotten some amount of electric field pointing that way. And what the charges accumulated here does is it adds to the electric field outside of the conductor, yielding this value, and it subtracts from the electric field inside the conductor, giving us a 0 electric field inside the conductor as required by static electricity condition. So this is the last of the applications of Gauss's law. I hope you see the simplicity of these calculations and learn to make this argument for yourself so that you don't have to do all that nasty integral you saw me do. Now, these applications of Gauss's law does have a limitation. Let me end with that. Is that it relies on symmetry. All the precise arguments we made, you cannot make them if you don't have symmetry. So this is actually good for you, because this means there's really only 3 types of symmetry that you can use Gauss's law on, and you saw all 3 right now: spherical, cylindrical, rectangular. So once you learn how to apply Gauss's law on each of those 3 symmetries, then you know how to apply Gauss's law in all possible situations. Until next lecture then, bye. Let me just use the 2-3 minutes to introduce this device that you will see a few times. It's called the Van de Graaff Generator. I'll leave the hair on this time. So let me actually show you what the Van de Graaff generator is made out of. The top here, it's actually very simple. I can even take off the top. It's a very simple device, empty here. And it's just a simple brush with, let me bring it closer to people. It's just a simple brush that connects to the metal half sphere inside. Good? So the top is really nothing complicated. Right? There's the belt is the only moving part in the top half of the Van de Graaff generator. So if you are thinking, that there must be all the interesting parts on the bottom half, well, you'll be wrong. This is the bottom half. So it does use electricity, but all that electricity is for this motor. You could run this with the hand if you crank it up. So this is a Van de Graaff generator. A big piece of it, what it is it's a metal sphere here, where inside of which is connected through this belt.
And what this belt acts as is, when I turn it on, the belt acts like a conveyor belt for electric charge. So what this brush you see on the bottom and the top are for, it's for bleeding of charge onto the belt. The belt will carry the charge up, deposit it there, bring it down. So this is a way of generating static electricity in a way that's safe and high voltage. This is one of the safe sources of a high voltage. So I have like less than a minute. Let me just do a quick demo that's, there's not a lot to explain, and it's just fun to see. Oh wait, I might have to get rid of the hair for that. Yeah, we'll do the hair later. Hair is for something else. All right, so that seems about good enough. Turn it on. So all that electricity, it's just going into turning that belt. Ooh. All right, let me turn off the light so that you can see better. You still can't see it. All right, let me make it darker. Yeah, you kind of have to be in the middle to see it. If we are here, all you will hear is the loud noise. By the way, Dino, you should be smelling something that's called ozone. That spark is it's producing ozone, which I guess is considered a pollutant. So, yeah. So that's one of the things that you can do with it. And believe it or not, this is all of this is relatively safe to work around. Really, the biggest danger you have with Van de Graaff generator is that when you touch it, and if you get a shock, it'll be painful because it's a shock still. It's like a static electricity when you take sweater off, but you don't worry that that's going to electrocute you. And if you have sensitive electronics, this could actually damage your sensitive electronics. So on Monday's lab, you will have some activity to work with this, and I think some of the traditional topics I lecture on, I feel like I'm not going to get enough. Let me give it a try. This is the Van de Graaff generator that you guys have seen before. You guys seen the spark flying across the thing. I'm putting this far away so that there won't be spark. But what that spark hopefully demonstrates is that this gets charged up electrically when I run it. So what I want to do is charge this up and place another object near it, see what happens to it. Turn it on. Charge it up, maybe. All right, it's getting charged too much. Oh, oops, turned it the wrong way. All right, that's as charged up as it's gonna get. All right, let's bring this in here. Yeah, that's what I was afraid would happen. Let me do it with a new balloon. I hope it's still charged up, and let me bring this new balloon near. Oh. Does it look like it's kind of sticking? Okay. Yes? A little bit. Not a lot. So, so I'm bringing it like this, and I bring it near enough, it kind of moves towards it a little bit. Right? And once it's stuck, then it kind of remains stuck. So, when I bring it near, sticks. Okay, I need to charge it up again. Let me. Okay, that's enough. And when I bring this near, it sticks a little bit. Oh, there. Right, sticks a little bit. You can see the attraction, right? Okay, so that's what you see with these balloons. And the second demo that I wanted to do involves a special arrangement. This time I'm just trying to discharge it so that I can touch it without getting shocked. What happened to, here it is. I have a very special device here. Can anyone tell me what this is that I'm holding? You saw that tab? Okay. That seems special. Let's see. So this is I actually have a demo video of this on the college's YouTube channel. But I will post it on the course website. So we have a setup of Van der Graaff generator and the grounded sphere here with the schematic diagram shown on the board with aluminum tab between them. And let's see what happens when the Van der Graaff generator is turned on. It's bouncing back and forth. It's not just getting attracted. Any guesses what's going on here?
I think it's being like attracted to one side and then being discharged and then retracts to the other side.
Yeah. So the distinction, now that's not what happened with the balloon. And this is the distinction that I need to draw. Okay, this is done. There's actually more part to do this demonstration. I'll post a video and you can look at the video and do that. But the distinction that I want to bring your attention to now and explain now is the distinction between conductors versus insulators or non-conductors. It's really the conductor aspect of it that we are interested in. So what do you think is the special property of conductor that sets them apart and makes us call them conductors? Like, what do you think defines a conductor?
Its ability to relatively allow electricity to flow.
Sorry, what?
Its ability to allow electricity to flow easily.
Allow what to flow? When you say electricity, electric charges, electrons. So, so I want to be careful because when you say electricity, do you mean electric force, electric field? Yeah, so that's how we define conductors. So conductors, they allow, let me be more carefully the exact phrasing, they allow electric charges to move within the conductor. Right? So it allows the electrons to flow from one side to the other if something makes them. But the key thing is they allow electric charges to move within the conductor. And there are some terminologies that you might see in your textbook, homework, that's associated with these electric charges that are moving. So, we talked about the atomic model. So when you see this conducting metal sphere, you know that there's way more electrons here than you can imagine, right? There's several, but with the conductors, what we are saying, we are not saying that all of those electrons move. There are some of those that move. So when we are talking about the electric charges that move, these are the two terms that you may see. There's a term that's referring to free charges. So that's talking about the charges within the conductor that are free to move. And I guess this is the more common term you will see. The less common term that you might see, especially in relation to material property, is something called conduction electron. And for our purposes, these mean the same thing. So free charges or conduction electron, they mean the same thing to us. So that's the distinguishing feature of conductors. What do you think the distinguishing feature of insulators is? It's that they are not conductors. They do not allow charges to move within the insulator. So that's why with the balloons, you saw that they were attracted to the Van de Graaff generator, and when they touched it, nothing interesting happened. Because charges are not free to, they don't go into insulators easily. So it didn't get charged when it touched the Van de Graaff generator, so it remained attracted. But with the aluminum tab, this is what you are seeing. If this is the Van de Graaff generator, let's just say this is getting charged to positive charges. And this is the other sphere. It's actually connected through the wire that's on it to the ground. And because it's electrically connected, this actually does get charged as well. This gets charged negatively. And when you had the aluminum tab hanging between them, the important thing about this tab is that it's a conductor. Does everyone have a sense of what material is conductor, what material is not a conductor? So when you look at this remote, is this a conductor or insulator? Insulator. When you look at this ring, is it an insulator or a conductor? Conductor. What about this rack? Insulator. Okay, so maybe one more. What about this cellophane tape? Insulator. Okay, so what makes a conductor? Okay, what about this scissors? Insulating part, conducting part. So what part? What tells you that this is a conductor, even though you've never done experimental electrical experiment with it? It's metal, yeah. So if you want to think of conductors as metals, yeah, most conductors are metals. In fact, that's what makes them metal, because they're conductors. It's all related. So, so this is metal. It's made of aluminum, so it's a conductor. So this will get attracted to one or the other based on polarization. We didn't spend a lot of time with this in this class because I'm always skipping materials. But initially, at the very beginning, this has zero net charge, right? So when it's placed between these two, the first thing that happens to this is polarization. There's a separation between charges of that's within here. So it'll get polarized and get positive and negative charge on opposite sides. Now, depending on which sphere it's closer to, if it's closer to here, it'll get attracted to this sphere first. But the moment this tab touches this sphere, what happens to it? Now it gets positively charged. So it actually has a net charge. So the moment after it touches, now it gets repelled. And it goes, swings over to the negative sphere. And then now it gets negative charge. So it gets repelled again and back and forth. And it actually stops at some point. What would make it stop going back and forth forever? Like, what would cause it to stop? Like, so, I charged up Van de Graaff generator, and, I see it start moving, and I turn off the Van de Graaff generator, and you see it keep on moving, right? But, I have to imagine that it'll eventually stop at some point. Why would it stop? Well, why would it stop? Yeah, so this is actually carrying charges from one to the other, one at a little bit at a time. So when they are both all discharged, then it'll stop. So I'll post a video of a more detailed one on the website. You can look at it. But so I want you to bring your attention to this material property because it relates to what we have been talking about, electric field. We want to describe how electric fields and conductors sort of interact with each other. Let's say I have a region of space where I have set up an electric field. Don't worry about how I did it. I'm just telling you that I did it. So I have some region of space where I have placed electric field. The likely way I would have done it is by placing a plane of positive charges here and plane of negative charges here. That would have given me this electric field. But it doesn't matter. I'm telling you, I just did it. You don't have to worry about it. And what I'm going to do is I'm going to place a conductor within this electric field. So let's say I place a conductor, a conducting cube here. And the moment I place the conducting cube, things are going to start moving. So what I'm going to tell you is that I'm going to wait until things settle down. I'm going to wait for a static equilibrium to happen. Now, sometimes you never get to equilibrium, but here I'm just asking you to trust, we are going to get to equilibrium. So wait for that to happen. So once we are at equilibrium, and this object that I placed within the electric field is conductor, I want to ask this question. As a result of this conductor being present here, how would the electric field inside and outside the conductor have changed? Or does it need to change at all? Does it need to change at all? Like, can we be fine with the conductors here, the electric field is there, so there's some electric field inside the conductor, we are good. We don't need to do anything. Yeah, the way it's set up, I'm inviting the answer no, right? Let me briefly walk through the reasoning here, because this is one of the rules you are going to hear about conductors, and it's not some rule that's just made up out of nowhere. It does fall out of what we have been talking about here, the fundamental laws of electricity, and what we just introduced about conductors. The key thing about conductors is that there are charges in there that can move. Now imagine that I have one of those charges here, minus E, so that would be an electron. What would happen to this charge if the picture looks like this? It wouldn't move, right? Because you see the electric field, so field is to the right, so that means electric force is to the left, to this negative charge. So this will move to left. Oh, that's not static equilibrium. So I haven't waited long enough if that's what's happening. So this negative charge will start gathering on this side. And because the whole object is neutral as a whole, that means there's going to be essentially lack of negative charges accumulating on the right side. Where do you think it'll stop? Like at what point the charges will stop gathering? Like, so at how much polarization is enough that, all right, that's enough, no more charge moving? Like what one condition would you look for? No, the number, actually the free electrons, that's way less, no, it's not the number of electrons. That could be a limiting factor in like semiconductors or whatever, but most metals, there's just so many electrons you would never run out of them. Okay, let me ask you this question. As these charges move, do you imagine anything changing? Anything about the electric field changing? What happens with the electric field? What do you mean by slow? Oh, you mean the direction of the field line changes? Well, the way I've drawn here, I've done it carefully so that the direction wouldn't change all that much. But something about the magnitude might change. What do you imagine happening with the magnitude? Becomes weaker. Because if you are looking at the contribution from these charges here, you will have electric field pointing to the negative charge and away from the positive charge. Those are opposing the direction of electric field that produced that charge separation in the first place. Meaning this electric field will get weaker as more charges separate. How much weaker can it get? Like, what's the limit? 0. Can it ever reverse the direction? Probably not. So let's make it 0. So imagine you have so much charge accumulated on these two surfaces so that you can say electric field here is equal to 0. So now if I have a charge here, is this charge okay just leaving over here and be at static equilibrium? Like this charge that's here, do I need to worry about, oh, that's going to start moving and it's not going to be in static equilibrium? No, right? I mean, the electric field is zero, meaning there's a zero force on it, so it doesn't need to be pushed one way or the other. So now this is a static equilibrium. So this is the association I want you to make. When you have a conductor placed inside some non-zero electric field, then when you have reached the static equilibrium, because we are dealing with electrostatics, we are always going to be dealing with static equilibrium up until like last week before exam 2. So when we have all of this, you are going to have zero electric field inside the conductor. So this is one of the rules about conductors. There's actually one more that two more that I'll tell you eventually, but this is one of the rules. And the reason I want you to explain it, it's not some rule that somebody just made up. It's a natural rule that follows from the property of conductor. Okay? Okay, so that's the bit about conductors and electric fields that I need to mention before we go too far. And we are going to bring this property in over and over. As we are as we are analyzing some problem, this property will come in handy from time to time. So it's good to keep this in mind. There's one thing I want you to bring up as we wrap up Gauss's law. It's about application of Gauss's law to figure out some things about conductors. And I thought one good example would actually be this Van de Graaff generator. So this is the diagram of what you are seeing. So the sphere is simply a hollow sphere. And what it has is it has this conveyor belt, which is literally going to carry charge from the bottom up here, just mechanically, physically. It deposits it on the comb here. And this comb is hooked to the inside of this sphere. And that's how charge goes from this bottom, the source, onto the sphere. And so what do you think will happen to the charge? So let me draw this simplified picture that's a little bit larger. So this is a conducting shell. Essentially, I have some sort of mechanism to bring up, let's say, negative charges, some mechanism to bring up the charges and deposit it on the surface here. Once the charge gets there, what do you think happens to the charge? Collects there, stays there. Now, if, that could happen, and in fact, that would happen with the insulators. Now, if that's what happened, this is what will eventually happen. As the charges come up on this conveyor belt, they will get repelled from this comb, and you won't get any more collecting there.
Oh, so
yeah.
basically it
Yeah.
disperses itself throughout the entire
Yeah. So with the Van de Graaff generator, what you see is that, so what limits the amount of charge on the Van de Graaff generator? What limits the amount of charge on this? It's not the electrostatic repulsion between the charge you are bringing up and the charge that's already here. What limits the amount of charge here is actually how much charge is leaking through the air. This is a really beat up, not very shiny, not very good Van de Graaff generator, so it won't be able to keep that much charge. But if you have a really large Van de Graaff generator with a really smooth surface, you can keep a huge amount of charge, very large voltage of electricity there. So a key part of this, once you place the charge here, it moves. So why would it move? Like, why wouldn't it stay there? What's special? So remember, this is a conductor. What's special about conductor? It allows charges to move. I guess when you have only one charge here, maybe it's difficult for you to think, why would that single charge move? Well, all right, let's say there are 2 electrons instead of 1. What would these 2 electrons do? They will repel each other. They'll get away as far away from each other as possible. Let me think of one arrangement. One such arrangement would be this would go over here at this outer surface of the sphere. And this would go all the way over here at this outer surface of the sphere. Okay? So as we collect more charges onto the body of the conductor, where do you see them gathering?
along the outer surface.
Yeah, along the outer surface. And if this is a spherically uniform shell, then they would actually spread themselves out in a uniform way. That's the way they can, be spread out as far away from each other as possible. So that's okay. So we can say this much intuitively, that all this charge that's being brought up, they gather on the outer surface of the sphere. Now this is what I want to be able to mathematically prove. I want to be able to prove mathematically that on this inner surface of the sphere, on the inner surface of the shell, that there is no charge. Like, how would I prove that? So let me go through this. Yeah, you guys haven't seen it, so it's not fair for me to expect you to be able to guess it. This is another application of Gauss's law. Let's say you charged this up, so you don't have this conveyor belt of charges anymore. Let's get rid of the conveyor belt of charge, because that'll ruin my argument. So what you have is a spherical shell, a spherical conducting shell, on which you have placed some charge. And so we have some intuition that they are repelling from each other, so they might all go to the outer surface of the conductor. And the question one could ask is it really true that there's no charge at all on the inner surface? Well, to prove that mathematically, what I would do is I would apply Gauss's law. So the way I could do it is I can define this Gaussian surface. This time I'm not defining this Gaussian surface because I want to find the electric field there. It's because I know the electric field there. I would define my Gaussian surface something like this. Something that lies within the conducting shell. So no matter how thin the shell is, it's going to have some thickness. So I put my sphere, Gaussian surface, so that it's within some thickness of the shell. What do I know about the electric field at every point on the Gaussian surface? Chris? Zero. How do you know it's zero?
It's inside the conductor.
It's inside the conductor, yeah. We reasoned out the rule last time, right? The electric field inside the conductor must be zero. So here, nothing's changed. Electric field inside the conductor is zero. What do you know about so when you calculate the net flux, E dot dA, what do you know about E dot dA now? That's equal to zero, because your electric field is zero. The integrand is zero, so it's zero no matter what. What's on the right-hand side of Gauss's law? Yeah. What's on the right-hand side is the charge enclosed over epsilon naught. So the fact that electric field inside this Gaussian surface is zero, or the flux through this Gaussian surface is zero, means that the charge enclosed inside is zero. So what this is proving mathematically is that there's no net charge on the inner surface of the conductor. So then you can behave more like a mathematician and try to come up with, or devil's advocate, try to come up with a counterexample. What's some kind of situation I can come up with that sort of agrees with everything I've seen so far, but there's some kind of charge on the inner surface. Maybe it could be positive charges on one side and negative charges on the other side. Can you think of any argument to disprove something like this? Like that this cannot happen. Yes?
It seems like the charges would meet if it's positive and negative, they come together. Right?
They might. So yeah, I want more rigorous mathematical. So that's the physical argument. So if you're saying your intuition says that, all right, now I'm done, there's no charge inside, that's a good intuition. That's not incorrect. I just want to give you some practice on using mathematical argument for proof. It's similar to what you've been doing on Monday's lab. It's a very particular type of argument that you can make without long series of calculation for situations like this. Starts with S. We're not going to do any actual calculations. I keep saying mathematical argument, but mathematical doesn't necessarily mean quantitative. And also force doesn't start with the S. Well, you know, it is a static equilibrium, but no, something else. That was the whole point of the lab on Monday. Symmetry argument. So this is, you know, being able to use a symmetry argument well, it's almost like a magic. You just have to say a few right words, and you've proven something that would have taken you hours to calculate out by hand. So here, you know, I made things easier. We started out with a spherical shell. So it has a rotational symmetry, right? So that means if I take this sphere, if I rotate it 180 degrees around, then nothing should change. But if I had supposed any kind of charge separation like this, then I would have changed something where, you know, nothing else in the problem says there should be asymmetry like this. So using that symmetry operation, you can prove that charge distributions that look like this is not possible, because that would break the symmetry of the setup. So once you say there cannot be charge separation within the inner conductor, then now you're done. There cannot be any charge inside the inside of that shell. And that's really why when you bring in new charges, as you bring in new charges here, these negative charges are not opposed by anything. There's no negative charges on the inner surface. In fact, there's no electric field here at all. So as you deposit negative charge, it just goes on there freely, and then it almost immediately gets pushed out to the outer surface. And the next one, same thing as well. Question? Yeah.
Is there any way that some positive charge could come in through the bottom?
So it depends on the design. I guess, I don't know. This is the bit that I never really got. I think it depends on how, so the bottom part is designed so that this brush is either providing a positive or negative charge. There might be some voltage applied to it. So this is delivering one type of charge. It's not alternating between positive and negative.
I thought it was just getting out of the air.
I think usually there's some fixed voltage applied to it. Yeah. So it's the charges themselves are coming from the ground, but the way they're coming, yeah. So that goes into detail that I was never really all that interested in. But yeah, the belt is designed to bring only one type of charge, not alternate.
What I'm asking is, like, you know how there's arcing and making those.
Yes.
That's the whole thing. Could that happen internally? Could it arc from the charge outside to some positive charge inside? That would.
Well, so the arcing that you're seeing, it's something called a dielectric breakdown. So you are seeing the flow of electrical charge through the air. Now, air is an insulator, so why would they conduct charge? That's what happens when so you know, here outside there's an electric field, right? When this electric field gets strong enough, it can polarize air molecules to the point where it separates them. It separates electrons apart from the rest of, so it forms ion. It ionizes the air. Once the air is ionized, then it can now conduct charge. That's what you're seeing as a spark. Now, you know, electrons are elementary particles. Protons are elementary-ish particles. You cannot have arcing between electron and proton. Like, when you talk about positive charge, you're talking about protons.
Oh, very true. Yeah.
Right? Yeah. Good. So, you know, this is another example of application of Gauss's law, that you can use what you know here to conclude conclusively that inside this shell, there's no charge with the rigor of a mathematical proof. Yeah. So Gauss's law is useful when you are trying to do arguments with the conductors. Because with the conductors, one special thing you have is that you always know the electric field inside. even when you ruin some of the symmetry, you will know that electric field inside is 0. And that's sometimes useful when you're trying to make a Gauss's law-based argument.